Hi, I'm Janet Mitchell, and this presentation is designed for college undergraduates who are beginning to connect linear algebra with geometry. Today I'll be discussing linear transformations in both 2 and 3-dimensional space. These are the rules that describe how space gets moved, flipped, rotated, or stretched. I chose this topic because this is where linear algebra truly comes alive for me. Instead of seeing matrices as rows of numbers, we begin to understand them as tools that actively move and reshape space. Transformations take abstract calculations and turn them into something visual and intuitive, something we can actually see happening in the plane or in 3-dimensional space. This topic also connects to me personally. I'm a gamer, and I've always been excited about how math underpins virtual environments, from character movement to camera angles. That connection has grown even stronger as both of my kids have gone into fields built on these same ideas. My son is heading into computer game development, and my daughter has been working in 3D rendering with Blender since middle school. Seeing how reflections, projections, and rotations drive the visuals and physics behind the scenes has reinforced how relevant and powerful this topic is. So today, I'll walk you through the main types of transformations, what they are, how they work, and why they matter, both academically and in practical applications like computer graphics. Here's a quick overview of our journey today. I'll introduce what a linear transformation is and how matrices represent these movements in space. Next, we'll look closely at 3 specific transformations: reflections, projections, and rotations, along with a brief mention of scaling. After that, I'll walk through a simple worked example to show how students might demonstrate understanding. Finally, I'll connect everything to an application in computer graphics to show why this material matters beyond the math itself. Transformations create a bridge between algebra and geometry. They show how abstract matrix operations correspond to movements in 2 or 3-dimensional space. We're not just manipulating numbers, we're moving vectors, flipping space, and reshaping it in very precise ways. This is why transformations are so important in applications like computer graphics, physics simulations, and mathematical modeling. Once you understand how a transformation acts on the space, you can predict what it will do to any object built from vectors. The short clip from 3 Blue 1 Brown video reinforces this idea visually.
What formula do you give the computer so that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands? It turns out that you only need to record where the 2 basis vectors, I hat and j hat, each land, and everything else will follow from that.
The key idea is that a matrix records where the basis vectors land. Each column of the matrix shows where a basis vector goes, and from that information, the entire transformation is determined. That's why matrices are such powerful tools. The pictures show the geometry of the transformation, and the matrix captures that same information algebraically. This connection between visual movement and numerical structure is what makes linear algebra both intuitive and useful. If you'd like to watch the full video later, the link is included in this slide and in the references. Now that we've set the stage, let's go back to the contents page and move into reflections. Reflections are one of the clearest examples of how geometry and linear algebra line up. A reflection preserves the part of the vector that lies parallel to the mirror and flips the part that points perpendicular to it. That idea holds no matter what line or plane we're reflecting across. This example emphasizes that reflections aren't limited to the x or y axis. Any line in the plane can act as a mirror. What matters is not the equation of the line, but how vectors decompose into parallel and perpendicular components relative to it. The key geometric insight behind reflections is that only the perpendicular component changes, while the parallel component stays fixed. That's why reflected points end up the same perpendicular distance from the line, just on opposite sides. Even though the algebra for reflecting across a general line can look complicated, the underlying idea is exactly the same as the simple axis reflections students already know. The sticky notes highlight this. Reflecting across the x-axis preserves the horizontal direction and flips the vertical direction, while reflecting across the y-axis just does the opposite. Every reflection across an axis, a vertical line, or a slanted line can be represented by a matrix. The picture helps us see the geometry, and the matrix gives us the algebraic rule that performs the transformation. That connection between what we see and what the matrix does is at the core of linear algebra. I dropped a Desmos link here so you can play with it and see how the reflection behaves. Now that we understand reflections in the plane, we can extend the same idea into 3 dimensions. Reflections extend naturally from 2 dimensions into 3. The same principle still applies. The component of a vector that lies parallel to the plane stays the same, while the component perpendicular to the plane is flipped. What changes in 3 dimensions is not the idea, but the geometry. Instead of reflecting across a line, we reflect across a plane. Any plane in space can act as a mirror, and not just the coordinate planes. The important takeaway is that reflections are controlled entirely by the plane. The plane determines which directions remain unchanged and which direction is reversed. Points on opposite sides of the plane end up the same perpendicular distance away, just as they do in 2 dimensions. You can also see this directly in the matrices shown on the sticky notes. The entries that change sign correspond to the directions being flipped, while the entries that stay the same represent directions that lie parallel to the plane. The matrix is encoding the same geometric behavior we see in the picture. This visual reinforces that reflections are not limited to simple axes. They are geometric transformations defined by direction and orientation, and the same linear algebra framework applies in any dimension. I've included another link to another Desmos graph so you can play with it and see how the reflection behaves in 3D. Now let's take a look at something very similar, orthogonal projection. Orthogonal projection is a lot like reflection, but instead of flipping the perpendicular part of a vector, it just gets rid of it. I like to think of projection as a flattening of something, or casting a shadow onto a line or plane. In this diagram, each point drops straight down along a perpendicular direction until it hits the plane. Wherever it lands, that's the projection. That straight down drop is what makes the projection orthogonal. The key idea is that projection keeps only the part of a vector that lies in the plane and throws away the part that sticks out. Nothing gets flipped. We're just removing the information. You see this all the time in construction. Floor plans are a great example. A building exists in 3D, but the blueprint is a 2D projection. The height disappears, but the layout stays accurate. I've also included a Desmos link here so you can play with how a vector projects onto a line. So now that we've seen two related ideas, reflection flips the perpendicular part and projection moves it. Now we'll take a look at transformations that move space without flattening it. Rotations and scaling differ from reflections and projections because they don't remove or flip components. Instead, they move space in a consistent way. This clip shows one of the most important ideas behind rotation matrices. Rotations are determined by what happens to the basis vectors. By tracking where the basis vectors land, we can describe how the entire space rotates.
For example, in 2 dimensions, the unit vector 1, 0, that's my first so-called standard basis vector, when it gets rotated counterclockwise by theta, it ends up at a point cosine of theta and sine of theta. That's just the definition of what cosine and sine are. Similarly, the other standard basis vector, which is 0, 1, well, it rotates and ends up at the point minus sine of theta, cosine of theta. So what is the matrix for a 2-dimensional rotation? You just put those four numbers together, and this gives our matrix representation for a rotation.
That's why the rotation matrix has the form shown on the sticky note. It's not something we memorize. It's something we build directly from the geometry of how space rotates. This ties back to the earlier idea that matrices describe how space moves. Once the basis vectors rotate, every other vector rotates automatically in the same way. A rotation changes direction while preserving length, while scaling changes length while preserving direction. In both cases, the structure of space is preserved in a predictable way. If you'd like to watch the full video later, the link is included in this slide and in the references. Together, rotations and scaling complete our picture of how linear transformations can move, reshape, and organize space without flattening it. Now we're ready to look at a worked example. I chose this one because it shows how reflections, rotations, and translations naturally work together. In this example, a vector is reflected across a general line, y equals ax plus b. But before the video starts, pause and think about what transformations are needed to make this reflection possible. As the video plays, focus on how the geometry guides each step rather than the algebraic details. The goal here isn't to memorize a formula, but to see how geometric ideas translate into a transformation matrix. My example today for my presentation is going to be reflecting a vector across a generic line. So here's my generic line, and I'm going to call that my y equals ax plus b. And I'm going to take some random spot here, and I'm going to reflect it over that line and put it here. So this is going to be my vector xy, and it's going to find a new home over here at x prime, y prime. Now the easy one to do is a reflection across the x-axis. So if we were to get this point and reflect it across the x-axis, that matrix is super easy. So that's a reflection, 1, 0, 0, negative 1. So that keeps my x values, but then flips my y values for the reflection. So I want to pretend that this line here is going to be down here so that I can do the reflection. So that looks like we need to do a rotation. So I'm going to rotate this thing down. So our rotation matrix is going to have cosine and sine with a negative sign here
and another cosine there. Now, if you're paying attention, this is a positive rotation. I don't want to go in the positive direction. I want to rotate this down. So I'm going to take a negative, or not a negative, an inverse, right? So I can get the rotation going in the right direction. We're going to switch up these cosines and then switch up the sines. And normally we would check the determinant to make sure everything's good. So cosine times cosine, cosine squared, minus the sine squares. So that would end up being positive. Cosine squared plus sine squared makes 1, so we're good. So this rotation, inversely going in the opposite direction, is what we're looking for. Now, when we do that rotation, it's actually going to be floating up here, and this is a point of rotation. But I want that point down here. So we're going to do a little slide of negative b. So this is why I picked this example, because we got a little bit of reflection, rotations, and a slide. We're doing all the things. All right, so let's put this all together. We're going to take our xy vector, and we're going to slide it down. And we want it to be on the origin when it rotates, right? So this is our little slide. And then we're going to do our inverse rotation. So it's going down. We're going to go sine, cosine, cosine here, and negative sine. So this whole bit right here, I'm going to highlight it. This whole part is to pretend to be the x-axis. We moved all of the vectors and everything, so it's down here, so we can do our reflection. So our reflection matrix is going right here. 0, -1, 1, 0. So this was the whole point. This is the reason we're doing all the things. So we're reflecting across the x-axis. We moved this line, slid it down, and then rotated it, and pretend it's on the x-axis. We're going to do the reflection. So now we got to move it back, because that's where it actually is. This is just pretend, so we got to move it back. All right, so let's move it back. I'm going to pick a different color. So that means we're going to move our rotation back up. That means we're going to do a negative sine theta, cosine theta, cosine over here, and another sine here. And remember the little slide, we got to scooch it back up. So I'm going to scooch it back up, our little slide. And I'm going to highlight that so we remember what we're doing. This whole thing is to put it back. We got it? We got it all? So we're pretending this is the x-axis. We're moving this down, and we're rotating it down so that it's sitting on the x-axis. Do the reflection. Now that we've done that, we're going to scooch it back up, rotate it up, and put it back. Now let's do some math. So first, we're going to do the stuff in the parentheses, because PEMDAS, right? So I've got x, y minus b. And then just to make it easy, I'm going to take this stuff and stick it at the end, because that's an addition which happens at the end. So I'm going to call this my last bit. This is the last bit I got to do. All right, so let's copy some of this. We're going to do this part right here. So I'm going to be going left to right. Now these are all 2 by 2s, so it's not going to change anything. This is all not commutative, but associative. So I can do these in any order. It'll be okay. So cosine times 1 is cosine plus sine of 0. So that's 0. Oh, right here. So just in case we forget. So we want to do our rows first and then our columns in the second. So second row, first column. So sine times 1 is sine. And then cosine times 0 is 0. First row. So I got cosine times 0. And then negative sine times negative 1 makes it positive sine. Second row, 0. And then cosine times negative 1 makes it negative cosine. I'm going to copy down all of this. Ready for the next bit. We're going to multiply these together. So first row, first column, I'm going to get cosine squared, and then minus sine squared. Next up, sine cosine, plus, oh wait, negative and negative make positive. No, yeah, negative and negative make positive. So we've got sine, cosine again. Give us some space. Next up, first row, second column, cosine times sine again, sine cosine, and then sine and cosine again. So it looks like we got the same thing. So I'm just going to do a little sneaky simplifying in here. So that's 2 sine cosine. And then the second row, second column, so sine squared, and then subtract. We've got minus cosine squared. And then I'm just going to copy this down just to keep it clean. Right, plus 0b. If you've been paying attention, we've got all this theta, but I've got y's and b's and x's. So what we want to do is get it in terms of a. So I'm going to throw this into a really quick triangle, and all of this is going to be theta. A is a slope, so this is rise over run. So our rise is a, and our run is 1. Pythagorean theorem, we're going to get ourselves an a squared plus 1. And now we can rewrite all the things. So now this is sine theta is equal to opposite over hypotenuse, a squared plus 1. And I got cosine, that's going to be adjacent over hypotenuse. All right, so now we can put all that in here and stub it in. Ooh, I'm going to give myself some space. All right, so first up is cosine squared. So I'm going to take this n squared. So I got 1 over a squared plus 1 minus sine squared. So that's a squared over a squared plus 1. Remember, all of this is simplified here, so I'm going to do that. So I'm going to get 2 sine is a over square root a squared plus 1, and cosine. Oh, look at that. It's the same thing. So 2, I'm going to do some sneaky simplification here. So when we multiply the bottoms, the square root's going to go out. So let's put 2a over a squared plus 1. And then this is the same, only flipped. So now this is a squared minus 1 over a squared plus 1. All right, now we've got this all in terms of a. And we want to multiply this by y minus b and a little bit. So when we multiply, we want to take the whole first row times the column, and then we end up with a 2 by 1 at the end. All right, more math. Here we go. So now I've got x times all of this. So remember, all of this is simplified right here. So instead of a squared minus 1, this is 1 minus a squared over a squared plus 1. Plus, we're going to take the bottom times this thing. So we've got y minus b, and all of this 2a over a squared plus 1. So this is all one row. Second one, remember, this is simplified here. So I'm going to take x times all of this, 2a over a squared plus 1, plus y minus b times all of this, a squared minus 1, a squared plus 1. Getting messy. All right, there we go. Oh, did I forget? I did forget. I got to put my little extra. So I'm going to put my little bit. This is where I'm going to put it. Plus b. There it is. Looks good? So this is all for our new home, x prime, y prime. All right, and I should have put it right here. So under equations, see, I typed all that stuff in. And when you move your point, nope, that's not it. This is it. Oh, it reflects. Look at that. So all of that I just showed you, I just typed it in here, even with the little plus b at the end. And it shows our reflection. Not that one, this one. Cool, right?
The most visible result of the use of linear algebra might be computer imaging and animations. Linear algebra is what makes 3D animated worlds and CGI come alive. Every explosion, camera pan, or animated character is built on matrix math. In fact, the reason that graphics cards are so important in video games is that they do matrix multiplication thousands of times per second. Why does that matter? Because every time you move around in a 3D world, the computer has to do a bunch of matrix operations to figure out which pixels in the 3D world show up where on your 2D screen. This is the same problem that 3D printers and animating software have to solve. How do these softwares decide what to display on each pixel of your screen when all it has is a web of 3D points to work with? The answer lies in matrices. And in this video, we'll explore a powerful way to think about matrix multiplication. Multiplication as a transformation.
Seriously, every time you watch an animated movie or show, see a commercial, or play a video game, linear algebra is working behind the scenes. Almost everything that's computer generated lies on vectors, matrices, and transformations. If you want to watch the whole video, the link is here on the slide and in my references. The article, The Role of Linear Algebra in Computer Graphics and Animation, from the website understandthemath.com, explains that objects in animation are built from points and vectors, and matrices are what tell the computer how to move, rotate, scale, and project those objects onto the screen. Characters don't simply move. Their positions are updated using transformation matrices, frame by frame. This applies to everything from rotating a character's arm to moving a camera through a scene to projecting a 3D world onto a 2D screen. The same transformations we've been studying, reflections, rotations, scaling, and projections, form the backbone of modern computer graphics. This kind of step-by-step transformation isn't just an exercise. It's how computers move and render objects in graphics, and when these transformations work together, their power really shows up. This connection between linear algebra and graphics is also reflected in university-level computer science courses, including Boston University's curriculum, where transformations form the core of the graphics pipeline. I've included links to both the article and the Boston University materials here on the slide and in my references. So linear algebra isn't something we just study in isolation. It's the language computers use to create motion, depth, and realism in the visual worlds we interact with every day. That's my presentation. Thank you so much for being here. Have a great day.